about transversality for multiple covers. So I want to ask the following question. What can be said about regularity of multiple covers without abstract perturbations? So I should try and clarify that my goal here is different from what you usually hear about from people's approaches to abstract perturbations for defining Gromov-Witten theory or symplectic field theory, all these invariants in full generality. I've given you already a sketch of how you define Gromov-Witten invariants for semi-positive symplectic manifolds, which did require some relatively weak form of abstract perturbations. I want to talk about what can be done without that. And there's a couple of motivations for this, which I'll just mention in passing very briefly. So you may have heard of something called the Gopakumar-Vafa formula, for example. And which in some form was proved very recently by Ian Allen Parker. I'm not going to write it down, but it's a formula that gives a relationship between Gromov-Witten invariants corresponding to different covers of the same homology class. And you can interpret it in some sense as a relationship between the count of simple curves in a symplectic manifold and the various multiple cover contributions corresponding to those curves. So that's a notion that wouldn't make any sense at all if you start out by doing abstract perturbations and then make the whole notion of multiple covers meaningless. Right? You have to first be able to define this notion of multiple cover contributions. And then it turns out that in Calabi-Yau threefolds, you see this numerical relationship between different Gromov-Witten counts that would just be invisible if you started out with the abstract approach trying to define the theory in full generality. So that's one example. Another example is Taubes developed some of these methods to attack multiple covers, as with the bifurcation picture that I drew earlier, in order to define this so-called Gromov invariant. And that was meant to be kind of a holomorphic curve version of the Seiberg-Witten invariance for symplectic four manifolds. There's a contact three-dimensional version of that called embedded contact homology. So this is something that's been studied a lot by Michael Hutchings, and also in part by Taubes. And it's an incomplete theory as things currently stand, because the only reason we know it's an invariant of contact three manifolds is that Taubes proved there's an isomorphism from this theory to Seiberg-Witten Floer homology. There should also be a proof of invariance of that theory that comes from the definition of a cobordism map. For a symplectic cobordism between two contact three manifolds, there should be a way of counting holomorphic curves that gives you a map from the ECH of one of those contact manifolds to the other. But we don't really know how to do that yet, except in some weak form by deforming things so that it looks very similar to the Seiberg-Witten equations and then getting information out of Seiberg-Witten theory. The problem with just doing it in terms of holomorphic curves is that somehow, whatever that map is, it has to count multiple covers in some fashion. So you have to have regularity results for those multiple covers, and you have to understand bifurcation theory for multiple covers so that you really know how to count them in an invariant way, the way Taubes did with the Gromov invariant. So these are just a couple of motivating ideas for why you might want to try and understand, well, in what circumstances could we actually prove that a multiply covered holomorphic curve is regular, despite the proof for simple curves not working? Right? So I did the proof for simple curves at the end of the last lecture, and we saw very clearly at some point we needed to assume the existence of an injective point. It's something you don't have for a multiple cover, and that's why the proof fails. But it doesn't mean that the theorem is always false. Sometimes it turns out to be true. So let me give a few examples. First, here's a non-example, but it pertains to the previous discussion about super-rigidity. This is again in the Calabi-Yau setting. So we take n equals 3, meaning we're in dimension 6, and assume the first Chern class of the symplectic manifold vanishes. So the index of our holomorphic is 0. But if we have a curve that's multiply covered, u equals v of phi, then we made this observation that the moduli space M of j near u contains a manifold of dimension 2 times the algebraic count of critical points of the branched cover. So in particular, that means u cannot be regular if phi has branch points. And we already talked about what you can hope for instead. The best result you can get if there are branch points is this super-rigidity theorem that I stated. Which is very good because then, in principle, you can still use these things to count holomorphic curves and compute Gromov-Witten invariants. Just instead of doing a literal count of holomorphic curves, you need to compute the Euler number of some obstruction bundle. This super-rigidity result tells you it's well-defined. So that's a situation where you can't have transversality as we usually understand it, but here's something a little bit simpler. Let's take, again, a multiple cover, u equals v of phi, where phi is unbranched. So in this case, the algebraic count of critical points is 0, which means the moduli space of branched covers close to phi is 0-dimensional. They're isolated objects. So the moduli space near u contains, again, this manifold of this dimension, but this dimension is 0. So actually, there's nothing wrong with that. If the virtual dimension of the moduli space is 0, this 0-dimensional space doesn't give you any contradiction. And actually, that's what's true if the underlying simple curve has index 0. But in general, so for generic J, we can assume the index of the simple curve is non-negative, because otherwise it wouldn't exist. The index of u in this unbranched case is always going to be the degree times index of v. So here d is defined as the degree of the branched cover, or unbranched cover rather. That's an easy consequence of the Riemann-Roch formula using the fact that phi is an honest covering map. It gives you a relationship between the Euler characteristics of the domains. So that's always a non-negative number if J is generic. Because again, we know that the simple curve V is regular. So if the index of U is guaranteed to be non-negative, it could actually be true. Well, add one more observation beyond that. Phi is isolated in the space of covers. So U could, in that case, potentially be regular. We don't have a proof yet that it is. But there's no obvious obstruction to it, just from these dimensional considerations. Okay. One more example. I'm going to apply a slightly unmotivated technical condition to this one, but we need some sort of condition. If we want to talk about branch covers, we know we can't always have regularity, but maybe sometimes we can. So again, U equals V of phi. And now let's suppose phi is a branched cover of Riemann surfaces with some number of critical values, call it r greater than or equal to 0. Critical values. And maybe it happens to be true that the index of V is greater than or equal to n minus 1 times that number r. Okay, so that's just a condition. Let's see what we can deduce from that. So if I denote by d sub z the branching order at a given point z in the domain of our branched cover, and I know that if you take all the z's in the preimage of some particular point, you add up these d sub z's, you'll get d, the degree of the cover. That is to say, sum over all z and phi inverse of zeta of these numbers d sub z equals d for all zeta. So let's compute something from this. The algebraic count of critical points, that's that number that appears over there in the dimension of the moduli space of branched covers. So by definition, let's take all the critical values zeta and then take all their preimages z equals, or z in phi inverse of zeta, and add up the branching order is minus 1. So the critical order in each case is 1 less than the branching order. So I need to add dz minus 1. Now, let's separate dz from 1. You notice that for each critical value, you're adding up the dz's for all the preimages of that one point. So that means for each critical value, you have a copy of the total degree d sitting there. That means that's d times the number of critical values. And then I have to subtract from that something which looks like sum over all critical values of, well, it's for each individual critical values, you have to subtract 1. So that's the number of points in the preimage of zeta. So in general, I don't know what that is, but it's at least 1 in each case. So this number in total is less than or equal to dr minus r, or in other words, d minus 1 times r. So what does that tell us about the index of our multi-covered curve? So if you plug in the Riemann-Roch formula for the index, and then you relate that to the index of the underlying simple curve using the Riemann-Hurwitz formula, that gives you the relationship between the Euler characteristics of their two domains. You end up with the following. The index of u is d times the index of v minus n minus 3 times the count of critical points, or yes, critical points, critical branch points. And so let's rewrite that a little bit. Let's put index v out in front, add to that d minus 1 times the index of v, and now I can say, by assumption, the index of v is at least n minus 1 times r. So I'll keep the first one separate, but over here I'm going to write this as d minus 1 times n minus 1 times r. And over here, I still have minus n minus 3 times the count of the critical points. I have also an inequality for that count of critical points, which tells me this whole thing is then greater than or equal to index of v plus, well, d minus 1 times r is in fact greater than or equal to the count of critical points. So I have that times n minus 1. And then I subtract n minus 3 times the number of critical points. What's left is 2 times the number of critical points. And that should look familiar, right? So that's 2 terms. The second one is the dimension of the moduli space of branched covers, phi. And the first one is the dimension of the space of simple curves, V. No, I lost the d minus 1 because it disappeared due to this relation here. Right, this term. Right. I mean, these details are not very important. And this is maybe, I don't know if this is the most natural way to come up with a result, but it does come up with a result, at least that I've been able to prove so far. What it tells you is if you have this numerical relation, then again, since this number turns out to be exactly the dimension of the moduli space of holomorphic curves of the form v prime of phi prime, so v prime is a simple curve close to v, and phi prime is a d-fold branched cover close to phi. Right? You know, of course, that that family of curves exists in a neighborhood of your given branched cover. So the index of your branched cover is at least that large. It means it is actually conceivable that your cover could be regular, because the kernel of its linearization will then be at least that large. All right. So again, you could be regular in this case. There's no obstruction. All right, now I'm going to state a few theorems that clarify these issues. So theorem A was the one about super-rigidity. Theorem B is a theorem about example B, namely for symplectic manifolds of dimension at least 4 and generic J, in example B, the cover is actually regular. Always. So for generic J, all unbranched multiple covers are actually regular. Sorry? Dimension 2, yeah, okay, I guess. Not very interesting, but true. The theorem C so for generic J, the holomorphic curve I talked about in example B is regular, right? So that's any unbranched cover. That's the statement. So I want to say something similar about example C, where I determined already it's conceivable that the branched cover could also be regular under this numerical condition. It doesn't seem to be always true. What I can say is the following. In example C, there exists some other holomorphic curve v prime near v and other branched cover phi prime near phi, such that u prime, defined as the composition of those two, is regular. So I don't know for a fact that a given branched cover will be regular, but I do know that I can find a regular branched cover nearby in the moduli space. All right, so my goal for the rest of today is first to illustrate the main ideas of why these theorems are true and why these ideas also tell us a little bit about the kinds of bifurcations that I mentioned earlier in Taubes' work. So, any questions first about the statements? So about the main ideas. To start with, I need to simplify my notion of regularity a little bit, and also the definition of super-rigidity, so that I can not always mention this somewhat complicated object d of d bar j, but talk about a single actual Cauchy-Riemann type operator. So that's called the normal Cauchy-Riemann operator. So first observation, if U is a non-constant J-holomorphic curve, then its critical points are isolated. So I should maybe specify this is a usage of the term critical points that's a little bit at odds with differential topology. You usually say a point is critical if its derivative is not a surjective map. Talking about holomorphic curves in a manifold of dimension at least 4, you can't ever have the derivative be a surjective map. But what matters is the derivative 0 or is it injective? It's going to be one or the other. So by critical point, I mean points where the derivative is 0. So these are isolated. And better than that, they have well-defined tangent spaces and critical orders. So the critical order I will denote by ord of du at z. That's always some positive integer for every critical point. The tangent space I will denote by T sub u at z, because that's the fiber of a vector bundle that I'm about to define. Right? This means, indeed, there exists a smooth subbundle Tu living in u star Tm, which at most points is just the complex one-dimensional vector space that's tangent to the holomorphic curve, wherever it's immersed. Okay? So the fiber of Tu at most points, z, is just image of du of z at all the non-critical points when du of z is non-zero. The point is that that bundle extends smoothly over the critical points. In other words, there is at each critical point a special complex one-dimensional space that that curve looks tangent to. Okay? It may approach it in a slightly strange way, because it will tend to wrap around it some number of times, and the number of times as you approach is exactly this critical order. So it's not hard to convince yourself in some concrete examples, like if you write down holomorphic maps from C to Cn in the form of polynomials or something, you can convince yourself that this is true at critical points. And it's a somewhat non-trivial consequence of various analytical results, such as the theorem of Mikolev and White about structure of singularities of holomorphic curves, that this notion extends for non-integrable almost complex structures. All right, so that's just a fact in the background. It means we can split this pulled back tangent bundle into that tangent, the bundle of tangent planes Tu plus something that I'll call the generalized normal bundle. So these are both complex subbundles. This defines what I would call the generalized normal bundle Nu over sigma of your curve. So of course, if U is immersed, that is just isomorphic to the normal bundle as you usually understand it. And another useful example to keep in mind, and actually for the super-rigidity problem, for instance, this is the only example you need to understand. If U is a multiple cover of V, and V is immersed, with normal bundle n sub v. Now, U in general will not be immersed. It'll have a critical point wherever phi has a branch point. But it's sort of obvious what the generalized normal bundle of U should be. You just take the normal bundle of V and you pull it back. And U is just phi star of NV. So that's somehow the most important special case. Okay. One observation, just as sort of a sanity check. The topology of this generalized normal bundle is somewhat delicately dependent on the behavior of the critical points. And you can see this by computing its first Chern number. So what would be the algebraic count of the critical points of view? So that's, by definition, the sum over all critical points of these orders, critical orders I just talked about. That's always some non-negative number. And one way to think about it is that du itself is a section of the bundle of complex linear homomorphisms from T sigma to this new subbundle Tu. That's a pair of complex line bundles. So this Hom bundle is also a complex line bundle. And the number of zeros of du is just going to be C1 of that line bundle. So that tells you the relation. This is C1 of Tu minus C1 of T sigma, which is just the Euler characteristic. Now, if you take the splitting of tangent plus normal piece and relate this to C1 of the pulled back tangent bundle, it tells you what the C1 of the generalized normal bundle is. So for an immersed curve, this would be C1 of the pulled back tangent bundle minus the Euler characteristic of the domain. But now we get this extra contribution from the number of critical points counted with weights. And we have to subtract. So in general, for a curve with critical points, C1 of its generalized normal bundle is smaller than you would ordinarily predict. Okay, so that's just to keep in mind that it does depend. If you move U around in the moduli space of holomorphic curves, its critical points may appear or disappear spontaneously. Okay, in dimension at least 4, that can always happen. If that happens, then the topology of this normal bundle will change violently, and that's something I have to be a little bit careful about later on. Okay? Now, the other thing that I want to get out of this discussion is look at the linearized Cauchy-Riemann operator, which I called d sub u in the previous lecture. That was a Cauchy-Riemann type operator on this pulled back tangent bundle, which I've just split into two pieces. So that splits this operator into block form. I can write it as du tangent part, du normal part, and then a couple of mixed terms, du tn and nt. So that is a first order differential operator taking sections of u star tm to 0, 1 forms on sigma with values in u star tm. But I split u star tm up into those two pieces on both sides, and then I get this block form. So this defines, in particular, if I look at the diagonal terms, Cauchy-Riemann type operators. DUT, that's an operator on the subbundle TU, and DUN on the normal bundle. So the second one is the one I'm interested in. This latter is called the normal Cauchy-Riemann operator of U. And the reason I'm interested in it is you can use this to characterize the notion of Fredholm regularity completely. So here's a theorem that I'm not going to prove, but I'll say a little bit about the intuition. Two statements, actually. So U is Fredholm regular if and only if its normal operator is surjective. So If you think about immersed holomorphic curves, this shouldn't seem very surprising, because with immersed curves, one way to understand the moduli space of all curves close to an immersed one is you can get all of them up to parameterization by perturbing your immersion along some section of the normal bundle. Okay, so every J-holomorphic curve nearby is obtained by such a normal perturbation of your immersion. You don't get to choose which complex structure you get on the domain. You're just looking for normal perturbations, which are other immersions with J-invariant tangent spaces. So you can set up the nonlinear problem in that way and then linearize it. What you find out is that the linearization of that is precisely this normal Cauchy-Riemann operator. Okay? So that's why surjectivity of this thing is equivalent to regularity. To see why it works when you have critical points takes a little more work. I don't want to talk about that. Second thing I want to say is that a simple immersed curve V is super rigid if and only if the normal operator dun is injective for all branch covers u equals b of phi. So the injectivity of the normal operator gives us a simple characterization of super-rigidity. And based on everything I've said, you can prove that just with a dimension count. All right, so at this point, the problem we have to solve is how can we establish that for generic J, the multiply covered curve we're interested in has a surjective normal operator, or in the case of super-rigidity, an injective normal operator. All right, so the next piece of this story is to talk about Cauchy-Riemann operators with symmetry. So this morning I sketched at least the proof of the theorem that if you restrict your attention to holomorphic curves that have no symmetry, that have an injective point, then for generic J they will all be regular. And we saw that symmetry somehow gets in the way of that proof. So the moral of that story is not that you shouldn't try to prove it in the presence of symmetry. It's that if you want to prove something like that, then you need to get whatever information is contained in the symmetry and think about it more carefully. Right? So in particular, the normal Cauchy-Riemann operator has a bunch of extra structure in the presence of automorphisms on a multiple cover that you don't otherwise see. All right, let's fix such a cover. I'm going to denote its domain by sigma prime j prime, which is unfortunately slightly the opposite of what I did before. Phi is a cover of that over sigma j, and V is a simple J-holomorphic curve. Phi is a d-to-1 holomorphic branched cover. And for simplicity, this is an assumption that I'll later be able to drop, but I'm going to apply it for now. Let's assume phi is a normal branched cover. So I mean normal in the sense of covering space theory. You may recall this means something about some subgroup of the fundamental group of something being a normal subgroup. The main consequence, I'll just write down, is it means this branched cover has as many automorphisms as it possibly could. In other words, the order of its automorphism group is equal to the degree of the cover, which is D. So given any pair of regular points that are mapped to the same point in sigma, there exists an automorphism of sigma prime that maps one of those points to the other. So that's certainly not true for all branched covers, but this assumption will turn out later to be harmless. I hopefully will have time to explain why. Let's denote by G this automorphism group. And just to be extra explicit, the automorphism group means the set of all biholomorphic self-maps of sigma prime such that phi equals phi of psi. Okay? If you remove the branch points and just think about honest covering maps, what we're talking about is deck transformations. All right. In order to exploit the symmetry present in the Cauchy-Riemann operator, I need to say a little bit about representation theory for this finite group over here. That automorphism group is always finite. So it has a finite collection of irreducible representations. And unfortunately, most people know complex representation theory, but that's not what I need, because this is not a complex linear operator. So I need to talk about real representations, which is everything you need to know about real representations can be derived from the complex representation, so that's not so bad. So let's denote by theta sub I. These are homomorphisms from G to the automorphism, real automorphism group of some vector space Wi. I equals 1 to n. These are the distinct irreducible real representations. G. Now, from complex representation theory, you may remember Schur's lemma, which tells you that for an irreducible representation, the endomorphism algebra, the G equivariant endomorphism algebra of your representation, is always isomorphic to C. I mean, all G equivariant endomorphisms are just obtained by scalar multiplication. So things are a little bit more interesting for real representations. There are actually 3 possible cases. Each of these representations has the G equivariant endomorphism algebra on Wi is isomorphic to what I will denote by K sub I, which is going to be, in each case, either the real numbers or the complex numbers or the quaternions. So my blackboard bold H is quaternions. Is basically the following possibilities. So how do you get, if you know all the complex irreducible representations, how do you get real irreducible representations? Well, one thing is you take a complex irreducible representation and just think of it as a real representation, because the complex linear maps on this vector space also are real linear maps. So that might give you an interesting representation. And it might indeed be true that its endomorphism, equivariant endomorphism algebra is exactly the same. So it might just be the complex numbers. Or it may be the case that your given complex representation is the complexification of some irreducible real representation, in which case the underlying real representation has R as its endomorphism algebra. Now, whenever you talk about a complexification, there is a canonical isomorphism between the complexification of a real vector space, or sorry, let me start again. Take a complex vector space, forget that it has a complex structure, just call it a real vector space, but now complexify it. That vector space is always canonically isomorphic to the original complex vector space direct sum with its dual. Okay? So in terms of representation theory, you have a similar result about complexifications of representations. And then you have an interesting dichotomy. Is that complex representation isomorphic to its own dual representation or not? If it is, you'll end up with the quaternions. If it's not, you'll end up with the complex numbers. That's all 3 possibilities. Those are everything that can happen. So if you've never heard of any of this before but actually want to read about it, there's the book by Sarah on representations of finite groups. It explains it all. I'm going to denote by T sub I what I call the type of the representation. It's either real type, complex type, or quaternionic type. We can encode that with the dimension of that endomorphism algebra, the real dimension. So it's either 1 or 2 or 4 in every case. All right, I need to make some room for the next statement. So I'm going to describe now the extra structure that your normal Cauchy-Riemann operator has for multiple cover. Each of these representations, theta I, determines a ki linear Fredholm operator which I'm going to denote by du superscript theta I, such that we get the following splitting, which I'll denote with a star. dun is isomorphic to the direct sum of, over all of these irreducible representations, some number of copies of these operators, du theta I, k sub I times, and I can also say what that number is. Ki is just the dimension over that endomorphism algebra of these representation spaces. So for each of the representations, right, the equivariant endomorphism algebra acts on the vector space Wi. It makes it a Ki module. So what I've written there is the dimension of that Ki module. And moreover, there's an action of the automorphism group on kernel and co-kernels of the normal operator by reparametrization. In other words, the automorphism group acts on the domain sigma by deck transformations. So you can compose any section in the kernel or co-kernel by one of those reparametrizations. And you'll always get something else that's still in the kernel or co-kernel. So we have this G action. That means it defines some representation of G. My claim is that it preserves each summand in the splitting. And if you just focus on one particular summand, for example, it acts on, say, the kernel of the operator du theta I repeated some number of times. So that's a particular subspace of the kernel of dun due to the splitting. G acts on that as a direct sum of copies of that same representation, theta I. So, Janko, you look very unhappy. Can I help you with anything? Oh, that's normal. Sorry. It's hard for me to help you with that. No. It's kernel and co-kernel are finite dimensional. That's the main thing I care about. I'm talking about a splitting of bounded linear operators on Banach spaces. Yeah. All right. No, they are finite dimensional. I mean, we're talking about finite groups here. This? Well, this is a finite direct sum of a bunch of bounded linear operators on Banach spaces, all of which are Fredholm. Yeah. Okay. So before I go further, let me give you a concrete example. This is all sort of very general, but there's a particular special case in which it's actually easy to understand what this splitting is. Let's look at branched covers of degree 2. So D equals 2, which means our automorphism group is just Z2. And let's denote its non-trivial element by psi. So what are the real irreducible representations of Z2? This is very easy to say. There are two of them. I'm going to denote them by theta plus and minus. Both are one-dimensional representations. They map the integers mod 2 to GL1R, also known as the non-zero real numbers. And you define them by sending the non-trivial element of Z2 to either +1 or -1. So theta plus is the trivial representation, theta minus is the unique non-trivial representation of Z2. Irreps, irreducible representations. So, according to my proposition up here, this gives us a splitting of the normal operator for a double cover as two pieces du theta plus plus du theta minus, and they're not repeated. These ki's are just the real dimension of the representation space, which is 1 in this case. They're one-dimensional representations. So we can actually say much more concretely what this splitting is. Actually, du theta plus minus is the restriction of dun to the subspace gamma plus minus of the normal bundle, which is defined as the space of either symmetric or anti-symmetric sections. In other words, all sections eta of the normal bundle such that when you compose eta with the unique non-trivial deck transformation, you get either plus eta or minus eta. So symmetric or anti-symmetric. That's what this splitting is. So let me make a useful observation about this. I haven't told you what the general case of the splitting is, so you shouldn't find it obvious that this has anything to do with the proposition I stated. But hopefully it's at least clear that this splitting is well defined, and that the fact of you having a Z2 symmetry implies that the Cauchy-Riemann operator is going to preserve these plus and minus spaces of sections when you define such a splitting, symmetric versus anti-symmetric. So one useful observation is that gamma plus of nu, that's the space of sections that are invariant under the deck transformation. So all of those sections actually can be defined by choosing a section of the underlying normal bundle for the simple curve and composing it with the cover. Right, all of these are of the form eta composed with phi for some eta, a section of the normal bundle of V. Remember, the normal bundle of U is just the pullback of the normal bundle of V here. So it's not too hard to derive from that that actually this restriction of the normal operator for U to that space of symmetric sections is fully equivalent to the normal operator of V. Oops. So du plus, or theta plus, is what I'm calling it, is equivalent to dvn, which means if the problem is to prove that dun is surjective, we've solved half of it already, right? We've divided dun into the sum of two pieces. The first of them is something we actually already understand, because we know how to prove that for generic J, dvn is surjective, therefore so is this plus part of dun. So the rest of the transversality problem for the double cover is to understand what happens for the minus part. All right, so the second main element in this story is what I call stratification. What time is this talk supposed to end again? 5:20. Yeah, it doesn't. No. 5:20. Very good. So here's a definition of another moduli space. I want to define some moduli space that consists only of multiply covered curves, but I want to define it in such a way that it has a nice structure, like actually a smooth manifold. This is not too hard to do. MdG of J is going to denote the set of all multiple covers of the form V of phi, where, first of all, V is a simple J-Holomorphic curve. With a little bit of extra structure, let's suppose that it has some marked points. Which are critical with prescribed critical orders. And V is immersed everywhere else. So this is just a kind of a bookkeeping device. Every conceivable simple J-holomorphic curve, V, is of this form if you choose the data properly. It has some critical points. They each have some critical order. I'm just supposing that we add to it some extra data of some marked points such that all the critical points are at those marked points. Phi, I'm going to do something similar with that. That's going to be a d-fold holomorphic branched cover with automorphism group isomorphic to G, and also marked points, which is where the branch points are, with each with a prescribed branching order. And also prescribed number of critical values. And no other branch points. And by the way, you can also, you're free to take the marked point sets to be empty, in which case we're just talking about unbranched covers or immersed simple curves or both. the point is, so 2 points. First, there exists a countable set of combinatorial choices defining such spaces such that every conceivable branched cover U equals V of phi of degree D with automorphism group isomorphic to G is in one of them. Okay? In other words, there's just a countable set of conceivable choices of what the critical orders of V can be and what the branching orders of phi can be and whether two of them coincide in the image and all that kind of data. So I've already kind of stratified the entire moduli space of branched covers. Each one of these also is a smooth manifold. Each is a smooth manifold for generic J. With dimension, well, its dimension in general, you can write it down, but the formula gets a little bit long. You have to be able to derive exactly what kind of dimensional constraint is applied by each of these critical order constraints and branching order constraints. So the dimension is determined by the combinatorial data. Okay? But the fact that it's a manifold should be clear, because you can move V around in moduli space of simple curves with marked points of prescribed critical order. That's something that's smooth and has some dimension you can compute. You can also move phi around in the moduli space of branched covers just by moving around the images of its critical values. So those are smooth manifolds. This forms actually a smooth fiber bundle. Their positions are not prescribed, only their orders. I probably said that badly. No, prescribed number of critical values. Only the number of critical values. So what I want to avoid is that you move your branched cover around such that some two critical points that used to have different images suddenly have the same one. Those are meant to belong to different versions of this moduli space, not the same one. Okay? So why am I making my life so complicated? Here's the important observation. The splitting that I wrote to the right and labeled with star over there varies continuously. As U moves in this moduli space. So, for example, U might move around because the underlying simple curve moves around. And I want to say that the splitting of its normal operator varies continuously. I'm already going to have a problem if V moves in such a way that one of its critical points disappears or changes critical order suddenly, something like that, because that changes the topology of the normal bundle on which that normal operator is defined. Yeah, that's not true. Ignore that. So prescribing the critical orders of V ensures that that normal bundle doesn't change its topology, which means the normal operators move continuously. If I'm additionally prescribing the branching behavior of phi, that ensures that its automorphism group is not going to change. And that helps me ensure that this splitting will also move continuously. Each individual operator in that splitting moves continuously. So in particular, they're all Fredholm, and their Fredholm indices don't change. Sorry? In a given stratum, the splitting, well, I mean, it might have some sort of globally non-trivial topology. That, right? I don't know for a fact that if I move around in a loop in the moduli space, that each splitting is going to come back to exactly where it was before. I mean, there might be some monodromy. I don't know if that exactly makes sense. Haven't thought about it very much. I'm just attempting a local statement about deformations. Okay. So now I can start to state the important part. Given a couple of integers, or a bunch of integers, ki and ci greater than or equal to 0, for I going from 1 to capital N, remember that corresponds to my list of irreducible representations. We define the following constrained version of this moduli space. MDGJ with respect to these collection of numbers k and c is defined as a set of all curves u in MDG of j such that the dimension as a ki module of the kernel of the Fredholm operator du theta I is exactly ki. And similarly for the co-kernel, dimension as a ki module of the co-kernel of that operator is c sub I. This is for each I from 1 to n. Okay? So let's make a quick note that if you just choose a bunch of integers at random, that space will usually be empty, because each of these operators that appears in the splitting has some particular Fredholm index, and that index had better be the same as ki minus ci. If you make a choice that doesn't satisfy that property, you've defined something, but you've defined the empty set. So the interesting case is when ki and ci are related to each other by the index of each of those operators. And now I can state theorem D, which is what makes the rest work. And it says that for generic J, this thing MDG with respect to K and C sitting inside MDG of J is a smooth submanifold of real codimension sum over the set of irreducible representations of the type of representation. That's, remember, that's either 1, 2, or 4, depending on real, complex, or quaternionic endomorphism algebras, times these kernels times co-kernels, ki times ci. So that's the formula. So let me just quickly tell you, I've stated this under the assumption that my cover is normal, that it has as many automorphisms as possible. But that assumption isn't necessary. I have to modify a few of my definitions if I drop that assumption, but it can be dropped completely. So the theorem is true in full generality and is useful in that way. Yeah. So let me try to explain a little bit what to do with this. Yes? For example. Right. So for example, yeah, if all the co-kernels are zero-dimensional, this is a zero-dimensional, zero-codimensional submanifold, so it's then just an open set. But it's a stratum of positive codimension if you choose either positive, well, if you choose both the kernels and the co-kernels to be positive dimensional. So you can attack transversality in this way by looking at positive co-kernels, or you can attack super-rigidity by looking at positive kernels. Either way, I'll give you a couple of examples. First, I can already sort of explain why theorem C is true. So theorem C was the statement that under some technical condition on dimensions. Let me state it again. The condition was we have a branch cover V of phi such that the index of the underlying simple curve is at least n minus 1 times the number of critical values of phi. So the claim was that under that assumption, you can always find some nearby branch cover that is regular. So I'm not going to do the computation for you. That would bore you to tears. But one has to do a bit of a computation at this point. And after you've done the computation, you find out the point of this technical condition here is that it guarantees the indices of all those special Fredholm operators corresponding to irreducible representations are non-negative. That's actually the whole point. I can tell you right now, if you want to apply these kinds of methods to understand transversality properties for multiple covers, the main thing you need to be able to do is to compute the indices of these Fredholm operators that appear in the splitting. What we get from this, so first of all, notice that according to this splitting, we should be very relieved right now, because if that weren't true, it would be completely impossible to ever get transversality. This normal operator couldn't ever be surjective unless all of those indices are greater than or equal to 0. You need all of them to be surjective at the same time. So if that weren't true, things would be hopeless. This is a necessary condition for U equals V of phi to be regular. Meaning DUN surjective. Is it actually sufficient? Well, that's not quite what theorem D tells us. What theorem D does tell us is that if U turns out not to be regular, then it belongs to one of the constrained moduli spaces in which one of the dimensions of the co-kernels is positive. And then this number is always going to be positive. So it's in a stratum of positive codimension. So that tells you, what should I say? Right, so by theorem D, this condition is also sufficient for all U belonging to an open dense subset of MDG of J. In other words, outside some strata of positive codimension. Okay. That's the proof of theorem C in a nutshell. Let me do a special case of the proof of theorem B. Theorem B is a stronger statement. It wasn't just that you can perturb your curve in its moduli space to find another one that's regular, but actually that for unbranched covers, regularity is guaranteed always for generic J. We have to do some sort of dimension counting to see this. The point is to show that if you weren't regular, it would again belong to some stratum that doesn't just have positive codimension, but its codimension is large enough to make it empty, to make its actual dimension negative. So let's see if that works. I'll do it for the special case. Excuse me. U equals V of phi with degree 2, and the underlying simple curve immersed. Oh, sure. Right, so the point is, your given branched cover might not actually be regular. But if it's not, then it belongs to one of these moduli spaces where you can choose one of the co-kernels to be positive dimensional. And this formula tells you that that submanifold has positive codimension in the whole space of branched covers. So it means if U doesn't happen to belong to one of these strata of positive codimension, then it will be regular. And everything outside of those strata is actually an open and dense subset. So for an open and dense subset of your moduli space of covers, you do have regularity. That's the point. Okay, so I'm going to look at an unbranched cover of an immersed curve where the cover has degree 2. Now I already know, of course, in the first place, that means that the multiply covered curve U is itself immersed. And then the index of that curve is just the same as the Fredholm index of its normal operator. I observed before that the index of the curve is just the degree of the cover times the index of the underlying simple curve. So that's 2 times the index of V. The normal operator of V also has Fredholm index equal to index of V. And of course, there's the splitting of the normal operator into the plus component and the minus component we already discussed, where du theta plus is actually equivalent to the normal operator of E. So its index is the same as that of the normal operator V, which is index of V. And now I can derive from that the index of the other piece. This is the step, by the way, that's much easier in the degree 2 case than in general. If I were trying to attack a more general problem, I would have more summands in the splitting, and I'd have to compute the indices of those operators individually. Right now, I can deduce it without attacking that problem so directly. I just have to say the index of du theta minus is evidently the index of dun minus the index of du theta plus. The former is 2 times index of v. The latter is index of v, so I end up with index of v again. All right, so that's the basic information that I need to know in order to plug it into that codimension formula up there. So the other thing, of course, that I already observed is that for generic J, du theta plus is already surjective because it's equivalent to the normal operator of the simple curve. So I just need to understand what happens to du theta minus. Now, if u is not regular, then du theta minus is not surjective. So u belongs to one of these constrained moduli spaces where, so I can assume C plus, of course, equals 0, because the plus part is surjective. C minus is some positive number. And the k's are related to those by the indices of the two operators. K plus is going to be, well, K plus minus is C plus minus plus the index of the operator du theta plus minus. In other words, both of those are index of V. So the codimension of this moduli space according to that formula over there is going to be some number t plus times k plus c plus plus t minus k minus c minus. Both of these numbers, t plus and minus, remember those are defined to be the real dimension of the equivariant endomorphism algebra of the representation. Both of those representations are one-dimensional. The representation space is R. So this endomorphism algebra is one-dimensional in both cases. Also, C plus is 0, so I can just drop that immediately. What I'm left with is T minus times K minus, which is, sorry, T minus is 1. K minus is C minus plus index of V. And that times C minus. Okay, that's the codimension. It's living inside some larger space whose dimension I now need to know also. And that's pretty easy because there are no critical points in the picture. So there's no marked points at all. This space M2Z2 of J consists of double covers U equals V of phi. V is simple and immersed. And phi is unbranched. So phi itself has no moduli at all. V moves in a moduli space whose dimension is just the index of V. So this thing has dimension index of V, which tells me the dimension of the constrained thing that my non-regular curve lives in is index of V minus this codimension up here, C minus times C minus plus index of V. Let's rewrite that as minus C minus minus 1 times index of V minus C minus squared. Because J is generic, so the simple curve necessarily has a non-negative index, and by assumption C minus was positive, so that number over there is manifestly negative. And that's a contradiction. Okay. So that's the kind of dimension counting argument you need to do. If you want to prove theorem B in full generality, the idea is essentially the same, but you need a bit more information. You need the indices of all of the operators that occur in the splitting, and you need the indices of every conceivable moduli space of simple curves with critical points that you might want to think about with various prescriptions of critical orders. And you need the dimension of the space of branched covers with all conceivable types of branching data. And then you just have to do a calculation and find out that the negative dimension for this constrained space whenever the co-kernel of some end has positive dimension. So I'll just mention it quickly now, as I don't think I'll have time for it tomorrow. You can similarly show by dimension counting if n is greater than or equal to 3 and index of V equals 0, then any branched cover V of phi with du of n not injective lives in a stratum of negative dimension. So that's what gives you the proof of theorem A on super-rigidity. Okay? So I just want to conclude today with one more remark about this Taub's bifurcation theory. We can maybe make a little bit more sense now of the picture I drew. So I drew a picture before that involved a generic one-parameter family of almost complex structures. And a parametric moduli space that includes some simple curves and some double covers. So if I try to be consistent about the colors, actually I don't remember what colors I used before, but maybe neither do you. So there was a family of simple curves that turned around at some point, giving us a birth-death bifurcation. And there was also a family of double covers, which were unbranched. And now we know that for generic J, those will always be regular. But of course, not necessarily for every individual parameter in a generic one-parameter family of J's. And there was this phenomenon we drew where that regularity fails at some point, and a new family of simple curves pops out from the double covers. So if you really want to understand why this happens and how it happens, the first thing you need to ask yourself is, unbranched double covers? Yeah. So this whole discussion about the moduli space of multiple covers and the constrained version with the kernels and co-kernels, you can do it all parametrically as well. And the codimension formula is exactly the same. The proof is almost word for word the same. I'll talk about the proof a bit tomorrow. In particular, you can write down a space I would denote by MDJ for the family of almost complex structures, also satisfying these co-kernel and kernel constraints. This is sitting there inside MDJ of the family without those constraints. Now, this is a space of pairs, parameter S plus a curve U, which is JS holomorphic for that particular parameter, but is also a default multiple cover with automorphism group G. And in the case at hand, that's always a one-dimensional space, right? This is the picture we've drawn of that space. Well, in particular, this one here, the green one, is that one-dimensional space. So if you want to see whether there's any element in this space for which regularity fails, since that's one-dimensional, you have to see which strata of this thing can have codimension 1. Well, in general, its codimension is sum over all the representations of type of representation times dimension of kernel times dimension of co-kernel. That's going to be 1 in exactly 2 circumstances. Case 1 is that the dimension of the co-kernel of the plus part of the operator becomes 1, but not of the minus part. So then the minus part of the operator remains an isomorphism. It's an index 0 operator in this situation. The plus part, well, that's actually equivalent, of course, to the normal Cauchy-Riemann operator for the underlying simple curve. So if that happens, it means that the simple curve is just failing for a moment to be regular. And that's exactly what we have right here. That's the birth-death situation. So this is a phenomenon involving the representation theta plus, the trivial representation. And of course, one has to do some more work to see that that's exactly what the bifurcation looks like. But the first part is to establish this transversality result that says in the moduli, in the parametric moduli space, there is a codimension 1 wall that we are passing through transversely. And then you have to imply the implicit function theorem, as Taubes did in his paper, to see that the structure of the moduli space in that neighborhood is this sideways parabola. Okay? Now, the other bifurcation comes from the other possibility. The other possibility is that the dimension of the co-kernel of the plus part is still 0, which means the underlying simple curve V remains regular. And that's why the picture of the green moduli space of double covers looks so nice. It's just moving smoothly along. The underlying simple curve is moving smoothly along. It remains regular the whole time. And we have a family, smoothly moving family of double covers over that. But there's a problem right here, which is that the dimension of the co-kernel of the minus part is 1. So the multiple cover is not regular. Which tells you that you need to, again, to apply the implicit function theorem somewhat more carefully to get a precise picture of what the moduli space looks like in that neighborhood. And the result turns out to be the degree doubling bifurcation. And actually, in Taubes' situation, those are the only two bifurcations that can occur, because Taubes was interested in counting embedded holomorphic curves plus certain doubly covered holomorphic tori. And if you're interested mainly in tori, you have a nice algebraic fact. The fundamental group of the torus is abelian. So the automorphism groups of these covers are always abelian, which means their complex representations are all one-dimensional, the irreducible ones. That narrows down very seriously the types of representations you ever have to think about. It turns out there's only these two. There's the trivial representation and the unique non-trivial representation of Z2. Anything else that you ever run into with one of these operators having non-trivial co-kernel, right? For instance, when we talk about du plus part having non-trivial co-kernel, that actually reduces to a discussion of a lower degree holomorphic curve. It reduces to a discussion about the simple curve V. Right? So that kind of phenomenon happens in general. For anything of degree higher than 2, whenever you see a co-kernel, you can actually reduce that to an observation about some lower degree cover. In the end, the only ones Taubes has to worry about are these two. There will be more general things that can happen with covers that are not tori, where the fundamental group is not abelian. And that's something that hasn't really been worked out yet. But based on the things that I've said, I think one can sit down and do it. So, but that's all I'm going to say about bifurcation theory, because that's all I understand about bifurcation theory so far. So what I will tell you tomorrow is mainly to fill in the details about how you define this splitting of Cauchy-Riemann operators beyond just the degree 2 case, and in particular why this stratification result theorem D is true. So for now, I'll stop there. No, no. In Taubes' case, there's no period tripling, degree tripling bifurcation, whatever you want to call it. It's because there is no irreducible representation that would give you that phenomenon producing a codimension 1 wall. Right? You have to understand what all the codimension 1 walls are that come from this formula. And the range of irreducible representations available to you when the group is abelian it's not that complicated. So it ends up reducing to really just these two possibilities. Yeah. Now, I mean, I do think that absolutely some sort of degree tripling or even higher degree bifurcation is possible when you talk about covers of genus greater than 1. As soon as the automorphism groups become non-abelian, then I think things will get much more interesting. But this has not been worked out yet.
Not, let's thank the speaker.